Assalamu alaikum. So today I'm going to start with a physical motivation of how we can achieve wells. Suppose you have a capacitor. The capacitor of course has two parallel plates, and then after some distance you place another capacitor, an identical capacitor. And you apply a voltage to the capacitor, identical voltage. So you apply a positive potential to this plate and a negative potential to the right plate. This voltage is some V0, and you apply an identical configuration to the other capacitor. This voltage is also V0. So as a result of this configuration, this plate becomes negatively charged, and this plate becomes positively charged. Likewise, this plate becomes positively charged, and this plate becomes negatively charged. Now in each of these plates we make a small hole, and we make a small hole in this plate, and the hole is small enough that if we prepare an electron and give it a certain amount of energy E as it comes off from a filament, this electron is injected, it passes through the holes and goes into this region. And once the electron has gone into this region, this hole is plugged. Now as this hole is plugged, this electron has a certain amount of energy, its energy is E, and now it is inside, it is trapped up to eternity inside the region between these parallel plate capacitors. Now if this point is x equals 0, if this point is x equals L, that is in between the middle point, the center point between these plates is x equals 0, and the center point here is x equals L, I would like you to draw the potential energy distribution for this physical configuration. What does the potential energy look like? So what I would like you to do is, I would like you to plot versus x the potential energy, and this point is x equals 0. One of the plates is here, the other plate is here, and then you have another point x equals L, and you have a plate here and a plate here. Just figure out what the potential energy curve will look like. I'm sorry, I've made this the other way. I've made this the wrong way. This should be negative, this should be positive. I'm sorry about this, and thanks for pointing this out. Question: if the electron approaches a negative plate, does the potential energy go up or down? Up. If it approaches a positive plate, what happens to its potential energy? It goes down. So this point and this point, are they at the same potential or different potentials? They are at the same potential because this voltage is identical to this voltage. So in between this plate and this plate, there is no potential difference. So the potential difference is a constant. And is the positive plate at a higher or at a lower potential with respect to the negative plate? Higher or lower?
नेगेटिव के पास ज़्यादा है, पॉजिटिव के पास कम है, उसका प्लस क्यू से बना हुआ है.
Just consider, to start off with, you may consider a single parallel plate capacitor, just one. This is a positive plate, and then we have a negative plate. If you discharge an electron inside the region between these parallel plates, will it like to go towards the positive plate or the negative plate? The positive plate, which means when it's closer to the positive plate, its potential energy is smaller, it's lower. And when it approaches the negative plate, its potential energy has to go up because it has to surmount a barrier. So for the electron, this negative plate is at a higher potential with respect to the positive plate. Therefore, and the potential energy increases linearly. Here the potential energy can be taken to be some number, say 0, and here the potential energy goes to its maximum value. Okay, because the potential energy is basically E, the electric field, dx. X goes from 0 to A, where this is x equals 0, this is x equals A. The electric field is constant, so V will depend linearly on x. In other words, for the negative plate, the potential is higher with respect for the electron, and for the positive plate, the potential energy is lower. So you get a curve like this, and here you get a curve like this. So this is a potential energy curve for this configuration. Now if we reverse the direction of the polarities, this becomes a negative plate, this becomes a positive plate, this becomes a positive plate, and this becomes a negative plate, then the potential energy curve starts looking like this. Okay, now if I move these plates closer together, then these dashed lines will move closer together, and the potential energy curve will start looking like this. If I move these plates even closer together, so this capacitor becomes thinner and this capacitor becomes thinner, these lines will become more and more sloped. Eventually, if I make this parallel plate capacitor to be of infinitesimal thickness, very thin, and the potential on each of these plates, so the charge on each of these plates goes to infinity, that is, I increase these voltages, I will get an approximation of an ideal potential well. This is how I can physically construct an infinite well, or an approximation of an infinite well. Now my question is, if this voltage is V0 and this voltage is V0 dash, and these voltages are not the same, what is the potential energy going to look like inside in this region? Is it going to be a straight line? No, it's going to be a sloped line. So if I have a potential energy curve, this is an infinite well. Something that we've already studied, we've solved the Schrodinger equation for this infinite well. Now I make another kind of well. It's an infinite well, but the floor of this well is not flat. Suppose the floor is sloping. What this physically means is that at the left, at x equals 0, you have a lower potential, and at x equals L, you have a higher potential. Which means that this plate has a higher potential with respect to this plate. In other words, this plate is more negative, has a higher negative charge with respect to this plate, because the electron sees a higher potential towards the right. So you obtain a sloping potential. Now what I would like you to think about is that if an electron is injected into such an infinite well, whose floor is now sloping, there is a gradient in the floor, and the electron that is injected has a certain energy E, right? Can the electron exist outside the well? First question. Can it go outside the well? It cannot, because the potential energy is going to infinity. The electron, no matter how large in energy it has, it will never have sufficient energy to overcome the potential energy, which is infinite. So it cannot go outside the well. So it is indeed an infinite well. The electron is bound to remain inside the infinite well. It cannot go outside. We know that for sure. Alright? Now the electron has some energy, E, and its energy has to be conserved. Please don't use your mobile phones. The energy has to be conserved. Its energy is constant. That's why I've drawn a straight line. This vertical axis represents some energy. The yellow line represents the constant total energy, and the white lines represent the potential energy. So white represents potential energy. Now what I would like you to think about is, if I were to solve the Schrodinger equation for this infinite well, what kind of wave function will I get? I've already done this in a tutorial, but for the sake of the entire class, I would like to do it again. If you have this infinite well, your wave function is like a standing wave. Okay? A possible wave function. Is K well known for this wave function? Is the momentum well known? Yes, the momentum is indeed well known. The position is not known. The position could be anywhere inside this region. The position is uncertain. There's a realm of possibilities for the position, but K is fixed. P is fixed. The momentum is well known. In other words, the wavelength of this wave does not change along the length of the well. Because we've already seen that the wavelength squared, or the wave number squared, K squared, equals 2me over h bar. And this comes from the Schrodinger equation. Now I would like you to think about what happens if we have a sloping potential. What does the wave function look like inside this kind of well? Just think about it, and if you can sketch the wave function, that will be ideal. First of all, let me write down the Schrodinger equation for you. I'm just writing the time independent part. what I would like to do, I would like to take this potential energy to the other side. When we were discussing the infinite well, we ignored this term. We didn't ignore it really because we took the potential energy to be zero. The potential energy was constant. We can choose any reference value we like, so we chose the potential energy to be zero. That's fine. But now the potential energy, even if it's zero here, it's sloping in the region of the well. So we cannot choose a potential energy zero. We can't do that. So the potential energy makes its presence felt. This is the first example where we are feeling the presence of the potential energy. Okay? Now if you look at this equation, and I will just take this variable to the other side, I obtain E minus Vx psi x. Now I multiply both sides by 2m over h bar squared. And I also multiplied with the minus sign so that this minus sign goes away and I get a minus sign here. Alright? Is this clear? Is it clear? आप पीछे बैठे ठीक है क्लियर है फाइन ऑल राइट नाउ इज E greater than the potential energy everywhere inside the well? Is E higher than the potential energy? Yes, it is. So E is greater than the potential energy. This is a positive term. Okay, it's a positive term. So all of this has to be a positive term. Psi of x, please. So all of this has to be a positive term, agreed? Because E is greater than V. The energy of the particle is greater than the potential energy. What is E minus V equal to physically? It's the kinetic energy. Because E is the total energy, V is the potential energy, the remainder is just the kinetic energy. And you will immediately recognize that this is 2m times the kinetic energy over h bar squared, which is just k squared. Okay? 2me is p squared. 2me over h bar squared is p squared over h squared, which is k squared. So this term, which I have written in square brackets, is just k squared, where k is a wave number. Okay? And since this is a square, it ensures that whatever I've written in the square brackets has to be positive, because the square of any number is positive. Hence, d square psi by dx squared is equal to minus k squared psi x. For an infinite well, how would the treatment be different? In which the floor is at constant potential energy. How would the treatment be any different? That will just be V equals 0. So it's still 2me over h bar squared is still the k squared. Now what's happening to the value of k squared? Is it increasing or decreasing? It's decreasing, because instead of E, we now have E minus a potential energy. Alright? So as this, in this case, k is constant, which means that the wavelength is constant, the momentum is constant, but in this case, the difference between the energy and the potential energy, which is just the kinetic energy, is gradually decreasing. So as you go from the left to the right, this difference between the energy and the potential energy is gradually decreasing, becomes smaller, even smaller, smaller, and so on. So your k is decreasing. So what's happening to the wavelength? The wavelength is actually going up. So now without solving this equation, can you graphically predict what the wave function is going to look like in this case? Can you please make a plot of the wave function, an approximate plot? ठीक है. अच्छा, मैंने हाइट्स के बारे में भी बात करनी है, एम्पलीट्यूड्स के बारे में, वो भी मैं करूँगा. ठीक है, सेम चेंज होगा एक्चुअली. क्वेश्चन समझ आया?
Yes, sir.
क्या हो रहा है वेवलेंथ को? इंक्रीज हो रही है, शाबाश. इट्स वेरी गुड, रियली वेरी गुड. वेरी गुड. मेरे ख्याल में शायद ही होगी. All right. So as the kinetic energy is going down, this term is becoming smaller and smaller, which means k square is becoming smaller, which means k is becoming smaller, which means the wavelength is becoming larger. So you have the same kind of solution. It's an EIKX solution or a sin kx solution, but the wavelength is no longer constant inside the well. The wavelength is going to increase as we go from left to right, but it's going to be zero at the boundaries because the boundary conditions haven't changed. The potential energy is still infinite, so the wave function has to disappear at the walls. So if I take this as a starting point, my wave function alright, let me make a clearer picture which shows the change in wavelength. The wavelength is smaller here, the wavelength is larger here. That's almost all you need to know. Now why is the amplitude increasing? Let me give you a hand waving argument for this. It's not really hand waving, but I can do it more quantitatively, but I can't do it in this course. The argument is that as k decreases as you go from left to right, what's happening to the momentum as you go from left to right? अब बताओ, मोमेंटम को क्या हो रहा है? डिक्रीज कर रहा है. ठीक है. So as you go from left to right, P also decreases. So if this were a particle and you consider it to be, and this was a quantum field or a matter wave, and the particle was actually moving in, you consider this particle to be actually moving inside the well, what would happen to its velocity as you go from left to right? Its velocity would also decrease. So when its velocity is decreasing in this direction, it would spend more time towards the right of the wall. It's just like playing musical chairs. If you have a row of chairs and you would like to occupy a chair and the music is running, if you would definitely like to occupy the chair, as you move away from the chair, you move faster. But as you approach the chair, you get slower and slower. You get slower and slower because you want to occupy the chair immediately. Exactly the same kind of argument applies here. If the particle is slower on the right hand side of this well, and if you were to measure the position of the particle, you would find it with a higher probability in the right hand side of the well. And that is why the amplitude of the wave function goes up, and hence the probability density function is also higher in the right of the wall. So as a general rule, if the wavelength decreases, the wave function increases in its amplitude. And the wave function, of course, is going to be zero outside the well, because the electron cannot exist outside the well. Another example. G. There is still going to be a whole number of wavelengths, or an integral number, integer multiple of lambda by 2, as they have in a standing wave. Okay? Question. I have a potential energy which is zero everywhere. And I have a single electron that is moving inside this region. What is the wave function going to look like? It's going to be a complex number in general, but what is the real part going to look like? If I have the Schrodinger equation, this is the Schrodinger equation. This is also the Schrodinger equation. Alright? I've just done manipulation. This is also the Schrodinger equation, provided k square is defined in this fashion. Now the potential energy is zero, and the energy of the particle is some positive number, E. Okay? And all of this energy is kinetic in nature. So of course, this is the Schrodinger equation. Hence this is the Schrodinger equation with V equals 0. Hence this is the Schrodinger equation. Hence this is the Schrodinger equation. So if this is the Schrodinger equation, can you solve what this, can you tell me what a solution will look like? It's going to be e power ikx. Right? E power ikx plus, the solution is going to look like A into E ikx plus B E minus ikx. Agreed? Yes. Alright. Now this represents, if a particle is injected from the left into this region, so I'm holding a particle, an electron, a photon, a neutron, an atom in my hand, I inject it inside this region from the left. Now it's going to move, if you look at it as a particle, the particle is moving from your left to right. Is there any reason why this particle can move backwards? No. In the infinite well, we had terms, an E ikx term plus a B ikx term, and B was minus A. Right? This gave us sin kx. So inside the infinite well, we had a term with a positive ikx and a term with a minus ikx. So this represents a wave that is traveling from left to right, and this represents a wave that is traveling from right to left. So what happens is that this wave travels from left to right, and there is a wave that originates by the reflection of the incident wave from the right wall, and that wave travels from right to left. So the two counter-propagating matter waves, they interfere, and when they interfere, they produce these standing waves. In order to produce standing waves, you must have confinement. You must have reflection from some wall. Alright? So standing waves are produced because inside the well there are two counter-propagating waves. One wave is moving from left to right, with the positive sign, and one wave is moving from right to left. There's a negative sign in the exponent. Okay? So in this case, a particle is injected from the left, it does not see any obstacle, no barrier whatsoever. So there is no chance for the particle to be reflected. So it has to have only this term, there is no reflection whatsoever. Okay? So for a free particle, which does not see any obstacle, no boundary, no reflection, there's only a matter wave or a field that propagates in one direction. The field is changing in time, of course, because with everything there is an E minus I omega t as well, that comes from the time dependent part of the Schrodinger equation, right? There is this time dependent part as well. So this actually means A E I k x minus omega t plus B E minus I kx plus omega t, and as you can notice, this equals E I k x minus omega over k t. This represents B E minus I k x plus omega over k t. But you also know that omega over v is just the phase velocity, right? For a free wave in which there is only one frequency, the phase velocity is the same as the group velocity. This is also a velocity. So here the velocity comes with a negative sign, here the velocity comes with a positive sign. Hence you can believe me when I say that this represents a forward propagating wave and this represents a backward propagating wave. Hence for a free particle, the wave function is just AEIKX. Of course I cannot plot this on the blackboard because it's a complex number, but I can plot the real part or the imaginary part. So if I were to plot the real part of this wave function, it's going to look like this. It's a cosine function or a sine function, which is the imaginary part. So this is the wave function of a free particle. Okay? Seem to be lost, a little bit lost today. Things are getting complicated. What does? What do they represent? This represents a forward propagating wave, whereas this represents a backward propagating wave.
The entire equation, the E of power negative I.
आपने कहां पे मेरा हाथ छोड़ा है? Where have you missed me?
Just after negative placement, the assumption you made.
I have made no assumption. Look at this equation, right? If I choose, okay, now be very attentive now. If you want to understand what's going on, I feel that you're lost a little bit. Do you believe this to be the Schrodinger equation? There's going to be a quiz, by the way, on Tuesday. Is this the Schrodinger equation? Yes. This is also the Schrodinger equation. This is also the Schrodinger equation. It's the time independent part. This is also the Schrodinger equation. Alright? Now if this is my equation, let me propose a solution. A trial solution is EIKX. Okay? Now you have to verify that this is indeed a solution of this equation. Can you find out what the left hand side is if this were the wave function? Please compute the left hand side for that equation when the wave function equals this. लेफ्ट हैंड साइड फाइंड करो. वो जो मैंने ऊपर येलो बॉक्स में लिखी इक्वेशन वो श्रोडिंगर इक्वेशन है ना, उसकी लेफ्ट हैंड साइड फाइंड करो व्हेन इफ द वेव फंक्शन इज eikx. माइनस के स्क्वायर आ जाता. So I propose that this is a solution of this equation. I have to verify it. So I look at the left hand side. The left hand side equals d squared dx squared of this solution, of this trial solution eikx. What do I get here? I squared k squared, which is minus k squared. Is this equal to the right hand side into eikx? Is this equal to the right hand side? Yes, it is. There's really no rocket science in this. Hence, this is a valid solution. This function solves this equation. Okay? So this is a valid wave function for a free particle. Now I propose another solution. Second trial solution. Suppose my wave function is e minus ikx, or my trial solution is e minus ikx. I have to verify that this is a solution. Can you verify this for me, please? The left hand side equals d square dx squared of e minus ikx. I get minus ik squared e minus ikx, and this again gives me minus k squared e minus ikx, which is equal to the right hand side. So is this a solution of the Schrodinger equation? Is this a solution of the Schrodinger equation? Is it? Yes, it is. I don't know why you're so silent today, why you're so laid back. Is it early morning? Both of these are solutions, they're valid solutions. Hence, if that is a solution and this is a solution, their composition, their superposition must also be a solution. Therefore, if I have that solution and I have an arbitrary constant with it, A, and I take this solution and I have any arbitrary constant with it, then this will also solve the Schrodinger equation. This will also be the wave function. Okay? मैथमेटिक्स हमें यहां लाके छोड़ देती है, ठीक है, क्योंकि मैथमेटिक्स एक हद तक आपको आगे लेके जा सकती है, उसके आगे फिजिक्स ने आपको लेके जाना है। अब फिजिक्स ये कहती है कि हाँ, मैथ्स ने तो ये कह दिया कि ये भी सॉल्यूशन है, ये भी सॉल्यूशन है, इनका सम भी सॉल्यूशन होगा। अब फ्री पार्टिकल को देखें, दिस इज रिप्रेजेंटिंग अ फॉरवर्ड प्रोपगेटिंग वेव एंड दिस इज रिप्रेजेंटिंग अ बैकवर्ड प्रोपगेटिंग वेव। फिजिक्स आपको ये कहती है कि देयर इज नो रीजन फॉर द पार्टिकल टू कम बैक, बिकॉज फॉर द पार्टिकल टू कम बैक there must be a force that is acting on the particle which makes it reflect, which makes it reverse its direction, which makes it accelerate. But there is no force acting on the particle because the potential energy everywhere is constant, and forces are, as you know, equal minus du dv by dx, right? This is something you've learned from mechanics. So if the potential energy is constant, dv by dx is constant, When dV by dx is constant, force dV by dx is 0, sorry, V is constant, this derivative is 0, so the force is 0. So you are injecting a particle like this. There's no reason why this particle should come back, because it's not seeing an obstacle. It can only be reflected when it hits a wall, a boundary, and the boundary transfers some of its momentum back to the particle so it can revert. So there's nothing that is keeping the particle from going on and on and on. It's going to move only in the forward direction. Hence, physics tells us that this term is 0 for a free particle. Maths tells us that both of these terms are legitimate solutions. But physics comes to our rescue and tells us, okay, maths provides you with this, but I don't have to take everything that maths has to say, because there is no reflection of the particle. So the solution of the Schrodinger equation for a free particle just represents this. Now if this is the wave function or the quantum field of this free particle, I can't plot this, but I can plot the real or the imaginary part. And that plot is going to look like this. Okay? Now suppose I have a potential energy distribution which is 0 here, but which takes a step. And a positive step of V naught. And now I have a particle that is injected from the left into this potential energy curve, into this region, and that particle has an energy E which is higher than V naught. Now what I would like you to do, I would like you to sketch what the wave function is going to look like. Shabash. ये ट्यूसडे को यूज है. Very good. No, उल्टा बना दे. Very good. Is the wavelength increasing or just remains constant here?
Constant.
Constant here. That is good, right? That's good. लेकिन ये वेवलेंथ इधर जाके चेंज हो रही है आगे. क्यों? पोटेंशियल एनर्जी तो चेंज नहीं हो रही.
ऊपर नहीं जा रही.
पोटेंशियल एनर्जी यहाँ पे तो कांस्टेंट है, यहाँ पे स्टेप आया है.
हाँ,
आगे पे कांस्टेंट है.
वो मैं बनाता सिर्फ एक पॉइंट पे लाके दे.
So you can plot wave functions by understanding what the Schrodinger equation means, but you don't have to actually solve the Schrodinger equation in many cases. So the wave function has a certain wavelength. When it reaches here, the difference between the energy and the potential energy decreases, K decreases, hence the wavelength goes up. And onwards the wavelength remains constant. Okay? Second example. If instead of a positive step you have a valley, the potential energy goes down. and the particle is again injected from the left. Then of course the wave function looks like this. Okay? Remember, I'm only talking about energy greater than V at all times. I'm not yet talking about what happens when the energy is less than V. Now I would like to ask you another question. I have the ground, and the ground acts as a mirror. And I have an atom at a certain height h above the ground, and this ground is an atomic mirror. So an atom comes and hits this mirror and is rebounced. Okay? These experiments have been performed in the laboratory. Yeah, 10 o'clock. So this is an atomic mirror, and this atom is being affected by a force of gravity. I would like you to plot what the wave function of this atom is going to look like. So it's at a certain height, it falls to the ground, rebounces, comes back up, falls back. So this atom is in an oscillatory motion. I would like you to plot what the wave function of this atom looks like inside this region.
It comes back to the same.
So that decreases and increases, decreases and increases.
You see, I would like you to plot the spatial profile of the wave function. You can't tell where the atom is at any time. It's everywhere. Since it's everywhere, I would like you to see what the wave function looks like. अभी बातें नहीं करने की इजाजत 10 बजे तक. ठीक है? तो इसको प्लॉट करें जरा इस वेव फंक्शन को. शाबाश. ये एक्सिस क्या है? मुझे स्पेस का चाहिए, टाइम का नहीं चाहिए.
नीचे जाते हुए बढ़ेगी, ऊपर जाते हुए कम.
शाबाश. पोटेंशियल एनर्जी कैसे चेंज हो रही है विद हाइट? अगर बॉडी को ऊपर रेज करें, पोटेंशियल एनर्जी इंक्रीज होती है, डिक्रीज होती है? इंक्रीज होती है. अब एनर्जी इज हायर देन द पोटेंशियल एनर्जी. सो इज द काइनेटिक एनर्जी इंक्रीजिंग और डिक्रीजिंग एज यू गो अबव? द काइनेटिक एनर्जी इज डिक्रीजिंग at higher altitudes. So now can you solve the problem? तो ये आगे फिर कम क्यों हो गया? नहीं, this is versus x. There is no time here. इन्होंने ठीक बनाया, उल्टा बना दिया आपने.
वेवलेंथ डिक्रीज होती है तो एम्पलीट्यूड इंक्रीज होता है, डिक्रीज होता है.
वेवलेंथ जब डिक्रीज होती है, एम्पलीट्यूड भी डिक्रीज होता है. In most cases. First of all, a plot of the potential energy. This is z, which is the height above the ground. This is a v. The potential energy is 0 on the ground and it increases linearly. Right? Here the potential energy is mgh. Remember, m is the mass of the atom, so it's a very small potential energy. Now, this is like a sloping potential. If this is the sloping potential and the energy is always higher than the potential energy, when this atom is at a higher altitude, the difference of the energy from the potential energy is small, because the potential energy is large. When the potential energy is large, then this term is small. When this term is small, k square is small. When k is small, the wavelength is longer. Hence, at higher altitudes, you have longer wavelengths, and at smaller altitudes, you have smaller wavelengths. So the wave function looks like this. This is what the wave function profile looks like in space. Now in Tuesday's lecture we're going to have a quiz, a very beautiful demonstration, and we're going to start looking at the effect or the phenomenon of quantum mechanical tunneling.